using the Turtle Sim Simulator, which is a great tool to learn and start learning about ROS. But once you have learned about ROS, it's now time to deal with more realistic and real-world robots. In this section, I'm going to introduce you to the TurtleBot 3 robot in a simulation mode, but also you can do the same thing in a real robot if you have already the hardware. I'm going to show you the different steps on how to install TurtleBot 3 robot in simulation environment, and also what are the different simulation options available for you to work with TurtleBot 3. And then I'm going to show you a small demonstration about these different environments. So I have here provided to you a simple guide to install TurtleBot 3. Of course, you can find the same instruction in the official website of TurtleBot 3 on Robotis website. But here I made just a summary because this information is actually spread in different pages and sometimes it is confusing to install the TurtleBot 3 simulator. So I put everything here in one place in the right sequence order, so you can just follow and try to apply on your computer and it should run and execute out of the box. So before installing TurtleBot 3, make sure to execute these two commands. First, you have to execute sudo apt-get update and then sudo apt-get upgrade. So make sure to make also the upgrade because the installation may fail if you don't do an upgrade in some cases. Then you can install the TurtleBot 3 package from GitHub. So first you need to go to the Catkin Workspace /src folder, and then you have to download these two repository from GitHub using git clone, and then you provide the following link. And then do not forget to put -b Noetic devel if you are installing on ROS Noetic. And you can change Noetic by Melodic if you work on Melodic, or Kinetic if you work on Kinetic, but I do recommend that you do all your installation on ROS Noetic, which is the latest version. So you install the first repository, TurtleBot 3_msgs. This will install the messages of TurtleBot 3, and then you install the core TurtleBot 3 package, and again you have to specify the branch here, it's Noetic/devel. And then you go to the Catkin Workspace and you do a Catkin make in order to compile everything. If you do so, you already install all the core packages of TurtleBot 3, and this will allow you to run TurtleBot 3, but not the simulator. Now, if you want to do for the simulator, you have to do just a few steps more. After the correct compilation of the Catkin Workspace, you can download the installation of the simulation packages. Okay, so you go to, again, to source folder in the Catkin Workspace, and then using git clone, and then you provide the link to the repository of TurtleBot 3 simulator, this one, and then you go to cd Catkin Workspace, and then you do Catkin make. And as such, you will be installing the TurtleBot 3 simulator. Of course, it has to be done in this order. If you try to install the simulator without installing TurtleBot 3 core packages or TurtleBot 3 message packages, in this case you will fail and you will have compilation errors. Then just after this, you can make the modification in the .bash rc file as follows. Okay, so you can go to the home directory and then write gedit.bash rc. So a good practice that I actually do, there are a lot of ROS launch commands for TurtleBot 3 simulator. There is the ROS launch for TurtleBot 3 fake, for teleoperation, for the empty word, for the maze, for also the house word. So sometimes it's maybe difficult to remember all of this. In my case, actually, I do some aliases like this. Okay, so for example, I do an alias burger, just for example, if I want to use the burger version of TurtleBot 3, because there are two versions, burger and waffle. Burger is the smallest one and waffle is the most comprehensive. And for this, if you want to use burger, you need to type export TurtleBot 3_model equal to burger. And if you want to use waffle, you need to type export TurtleBot 3_waffle. So I put this in the .bash rc file as an alias to burger and waffle. It will execute these two commands, and that will be much easier. And also, for example, you can use, I use the alias tb3 fake to launch the TurtleBot 3 fake robot using the command ROS launch TurtleBot 3_fake TurtleBot 3_fake.launch. I use the alias tb3 teleop ROS launch TurtleBot 3 teleop TurtleBot 3 teleop key.launch. And also for opening in the maze world, in the house world. Okay, this is optional if you want to do the same thing with these aliases. I found them very practical, and I can access all these different commands just by typing fewer letters. And if you want just to type the whole ROS launch command, you can just type it without doing these aliases. But what is important and necessary is that the end of the .bash rc file, you need, of course, to source the /out/ross/noetic setup.bash to activate the installation workspace, and you have also to source your Katkeen workspace to activate it. And then you can do export Turtlebot 3 model equal to Waffle if you want by default when you open the terminal, if you want to use a Waffle version. And you can change this one by Burger if you want to choose by default a Burger version when you open the terminal. So this will allow you not to type every time export Turtlebot 3 model equal to Waffle or a Burger, but it's going to execute automatically whenever you start any terminal. And at the end, you need to export svga underscore vgpu10 equal to 0, and this command will let to open Gazebo on a virtual machine and avoid crashing its display. If you don't put this, very likely Gazebo is not going to open if you use a virtual machine like I'm doing. So this one, if you look into the different forums, they will suggest to you to use this export instruction for Gazebo to open properly on the virtual machine. And that's pretty much it. Now, if you want just to use Waffle, put this export instruction, and if you want to use Burger, you can just put this instruction. But since you have already put in the .bash RC, you don't need to write it manually every time, at least for the version that you have put here. Having completed these instructions, you will successfully install the Turtlebot 3 simulator. And now let me take you through the different simulation environments that you can work in Turtlebot 3 simulator. So after installing Turtlebot 3, you can run it in simulation on different environments. So for example, you can run Turtlebot 3 in an empty environment, just an open space, like the case of TurtleSim, using the command ross launch Turtlebot 3 underscore gazebo, Turtlebot 3 underscore empty underscore world.launch. So this will allow you to open TurtleSim 3 in an open space. And this is like a straightforward application of the motion lectures that we have done in TurtleSim. So you can do the same thing, try to do the same thing as we did with TurtleSim, just by sending velocity commands in an open space to Turtlebot 3 robot instead of the TurtleSim robot. And if you have the real hardware, you can also try it on the real robot instead of the simulation, because the same code of the simulation should also run in the same way on the real robot. Okay, so this is the first environment. You can try it, you can make teleoperation using a teleop node that I'm going to show, or also you can develop the same motion applications that we have developed for the TurtleSim simulator. Okay, if you want just to play with this robot in the open space, you can also run the instruction ross launch Turtlebot 3 underscore teleop, Turtlebot 3 underscore teleop underscore key dot launch. It will run the teleop node, and then you can do the same thing as you did with TurtleSim. You can play around with this turtle in this open space. And of course, you can develop your own Python script or C++ code in order to make it move by sending velocity messages through using the twist message structure. Another also environment for the Turtlebot 3 is I call this as the maze environment. Okay, and you can run it using ross launch Turtlebot 3 underscore gazebo, Turtlebot 3 underscore world.launch. You will have this one. We are going to use this when we in the lecture of the laser scanner. So we will make some exercises on how to make the robot move without hitting these obstacles. So you can see here we don't have a completely open space. We have obstacles here that are shown in black, in green, and also some obstacles in the middle in the white color. So one of the exercises that we will do later in the laser scanner lecture is to make the robot move here around without hitting any of these obstacles. So you will learn this afterwards. Another nice environment also is the house environment that you can open using ross launch Turtlebot 3 underscore gazebo, Turtlebot 3 underscore house.launch. Here you have a more structured environment with different walls, with rooms, and you have a table here, you have doors. So here we're going to use this more when in the second course, in the SLAM and navigation course, you are going to learn how to build a map of this environment and how to make the robot navigate autonomously in such an environment. For example, going from this room to this room without hitting obstacles by planning a path and going through this path in a smooth manner. A very important tool is RVs, and RVs is used to make different kind of visualization. It's the ROS visualization tool. And there is a version for Turtlebot 3, which you can execute using Ross launch Turtlebot 3 underscore gazebo Turtlebot 3 underscore gazebo underscore rvs.launch. And here you can see, for example, one of the utilities of using RVs is to show the laser scanner. So you can see, for example, in this environment, when the robot is looking like this, there are obstacles. You can visualize them using the laser scanner data feed. Okay, like here, all these red dots represent the obstacles around the robot. And of course, you will learn in the laser scanner how to manage these kind of obstacles and how to avoid them while moving. You can also see the camera, so you can develop some computer vision application if you want. We are going to see this in more details with the OpenCV section. And here you can see more information about the topics available and different type of data that you can visualize in this tool. In addition, the Turtlebot 3 simulator offers a way to learn how to build a map for a particular environment. And for this, for example, you can run Ross launch Turtlebot 3 slam, Turtlebot 3 slam.launch, slam method, and here you can use Gmapping or cartographer. There are different type of SLAM algorithms, and this is going to be discussed in details in the second course, Ross for Beginners 2, Navigation and SLAM. And also you can run the teleop key, Ross launch Turtlebot 3 teleop Turtlebot 3 teleop key.launch, and then you can make the robot move, and while the robot is moving, is going to learn about the map of the environment and build it and save it as an image file and also as a metadata file in the YAML format. So these are the most important environments and capabilities of the Turtlebot 3 simulator, and we will be using Turtlebot 3 in the next sections related to OpenCV for computer vision, object detection for deep learning, and also the laser scanner. Okay, let's now make a simple demonstration to start Turtlebot 3 simulator. So I'm going now to start the Turtlebot 3 simulator in the world environment, in the maze environment. So this is the command, Ross launch Turtlebot 3 underscore gazebo Turtlebot 3 underscore world.launch. So it will take a little bit of time to open. Okay, now it has opened, and we can see now the Turtlebot 3. So this is the waffle version. Okay, you can zoom in, you can zoom out. Okay, and in the same way, we are going also to start the RVs using the command Ross launch Turtlebot 3 underscore gazebo Turtlebot 3 underscore gazebo underscore rvs.launch. Okay, and let's wait a little bit. So now we have RVs is open, and you can see here the Turtlebot 3. We can see the red dots, which represent the feed of the laser scanner. We can actually try to improve the visualization by improving the thickness of the points. So I'm going to put this at 0.04. So you can see these are the obstacles in the middle, and these are the obstacles that represent the wall in the perimeter of the environment, which corresponds to this environment over here. Okay, and then we can also open the teleop node to make the robot move using the Turtlebot 3 teleop Turtlebot 3 teleop underscore key.launch. Okay, and this is the node. So we need to use W, A, S, D, and X to move the robot. I'm going now to move the robot forward by pressing on W. So you can see that the robot is moving forward. When I press on W, I will press on S. The robot is going to stop. You can see also the robot moving on RVs. I'm going now to make the robot move forward. I need to activate this terminal. So now I'm pressing on W, as you can see, and the robot is moving forward. So you can visualize this in RVs, or you can visualize this in Gazebo. I will stop the robot now. I will make the robot rotate using the A key. Okay, you will see the robot rotating. And you can see also the laser scanner feed is going to be updated. Okay, when the robot is moving or rotating. Okay, so this is just to get started with Turtlebot 3. Of course, like any other robot, you can do ROS node list. And these are the list of nodes that are running. Okay, so the robot node is called Gazebo here. And you have the Gazebo GUI. You can make ROS topic list. You see the list of topics. Okay, and here we have the scan topic. We discussed this in more detail in the laser scanner lecture, and you can see the different other topics available over here. Okay, this was just a very quick and brief overview about Turtlebot 3, which we are going to use in the next lectures with OpenCV and also with laser scanners. In the previous lectures, we have presented the motion of the robot and how ROS represents the motion commands to make a robot move. However, what we have done so far is kind of a blind motion without awareness about the surrounding environment of the robot. In real applications, it is mandatory that a robot perceives the environment around it and extract useful information from the environment to be able to plan his motion and act in an appropriate fashion. This is referred to as robot perception, which is a popular field in robotics based on computer vision. Computer vision includes methods for acquiring, processing, analyzing, and understanding digital images. Typically, a robot uses a camera to see the world around it, and this camera will provide the robot with a feed of images that it needs to process so that to extract useful information. Image processing is a very complex and challenging task. Fortunately, in the last 20 years, a lot of research has been done and significant advancement took place. It is now possible to accurately analyze the content of an image and extract useful information out of it. The most popular library for computer vision and image processing is OpenCV. It provides a comprehensive set of tools and algorithms to perform complex operation of image processing and computer vision in real time. The objective of this lecture is to give an overview about OpenCV and its important feature. So OpenCV is an open source computer vision library. It was released under the BSD license and it is free for both academic and commercial use. It supports multiple programming languages, namely C++, Python, and Java, and works under different operating systems, including Windows, Mac OS, Linux, iOS, and Android, which has a strong focus on real-time, since it was written in C++ and has been optimized. OpenCV can perform a lot of operations related to computer vision. This is a sample of these operations. It can do 2D image processing. It can also perform image input and output and video input and output. It can read images from files. It can read video streams coming from USB cameras from video files. It can perform camera calibration, video analysis like motion extraction, feature tracking, foreground extraction. And nowadays, with the advances of machine learning and deep learning technology, it is possible to accurately perform object detection and also recognition. OpenCV also supports GPU-accelerated computer vision. It has much more functionalities. So let's see a couple of functionalities that we can use with OpenCV. One of the basic functionalities of OpenCV is to do image segmentation. So image segmentation is the process of partitioning a digital image into multiple segments, and it is used to locate objects and boundaries in images. Another operation is image thresholding, and thresholding is the simplest method of image segmentation. It allows to transform a grayscale image to a binary image. So the idea here is to take a color as a threshold, and any color above the threshold will be considered as white, and any color below the threshold will be considered as black. So the resulting image will be binary, either black or white. With the advances of machine learning and deep neural networks, it is now possible to detect and recognize objects inside an image. And this technology has promoted a lot of applications, like, for example, autonomous vehicles, which deeply rely on computer vision technique to observe the world around them. It is also possible to do nice drawing with OpenCV. For example, it's possible to draw circles, lines, polygons, text, and many different shapes. In the practical lecture, we're going to do a little bit of drawing. Edge detection is also an important operation in computer vision. It consists in finding the boundaries of objects within the image and works by detecting discontinuities in brightness. Edge detection is used for image segmentation and data extraction. One of the very useful functionalities in OpenCV is that to read and write images and video streams. With OpenCV, it becomes very simple to read an image and load it into a data structure for further processing. This was a brief background on OpenCV functionalities, and now let's move to the practical part of this section. In this lecture, I'm going to show you how to install OpenCV for ROS. Actually, it's pretty much simple, so let's see how it works. Of course, I assume that you have already ROS installed. In my case, I have ROS Kinetic. It's possible also to install any other version, although there could be some differences between the versions of OpenCV used in the different versions of ROS. So for example, here in ROS Kinetic, OpenCV version 3 is being used. So in order to install OpenCV, it's simple. Open a terminal. Then first of all, update your system. Sudo apt-get update. It should take some time to update your repositories. Now the system is updated. So later on, you can install OpenCV by using sudo apt-get install ROS, the version of ROS you have. In my case, it's Kinetic. Then OpenCV. So you can see I have OpenCV here, yes, and it is already installed in my system. So in your case, it's going to install OpenCV into your system. You can verify if OpenCV is installed or not. You can use Python here, and then import CV2. So if you don't receive any error, it means that you have everything installed correctly on your computer. Import CV2, it means import OpenCV library in Python. You can exit now. We will also need some additional tools. We need also to install the USB camera ROS package, and this is also simple. First of all, you need to update your system, and then you do sudo apt-get install ROS, your ROS version, then USB cam. Okay, so in my case, it's already installed. And also make sure that you have image view. So you can try to install the ROS version, and then image. So image view allows us to view images from USB or from other image topics in ROS. So I have already installed. So that's pretty much it. These are the different tools that we need, and now we are ready actually to start the practical part of OpenCV with ROS. This is the first practical lecture about OpenCV, and just to explain the roadmap, first of all, I'm going to start with presenting some of the most important features and functionalities of OpenCV through illustrative examples and demonstrations. And later on, I will present how images are represented on ROS and how they can be handled by OpenCV for further processing. So the next couple of lectures, I will be talking about pure OpenCV without ROS. And then I will talk about how OpenCV was integrated to ROS and how images collected from ROS topics can be read and processed by OpenCV libraries. One of the basic functionalities of OpenCV is to open and save images from files. So let's see how it works. So let us open Visual Studio Code, and here in the ROS Essential Projects, let's open copy.py. So this is a very basic Python script in OpenCV that allows to read an image from a file and then save it into another file. So first of all, looking at the directory, topic 3 perception. So here we have images. We have a tree image, we have a flower image, and we have a chess image, and black and white image. And this is the directory that we call copy, where the copy are going to be pasted. So let me remove these copies first, so we don't have anything here. Images copy. And then let's look at the script. So first of all, we have to import NumPy. NumPy is a data structure that will handle the image. So it is a library for scientific computing, and it can handle multi-dimensional arrays. So this structure is going to store all the pixel values of an image. And then we import OpenCV, import CV2, and finally, so let's specify the image name that we want to read is equal to 3, okay, and then we will call the method CV2, which is imported dot imread, means imagery, and then we have to specify the path to the image. So here I'm going to read the image in the folder images and image name, which is 3.jpg. This one, so this is now the folder image, and this is 3.jpg. Then with OpenCV we can create a window where to display the image. So CV2.named window. Here we specify the name of the window. I'm just going to call it image. And here we have the flag CV2.window normal. It means we can resize manually the window. And finally, we give an order in order to show the image. So here, ImShow means image show. We're going to show this image. And this is the name of the window where we will display the image. And finally, we will wait for a key to be pressed. When a key is pressed, we will execute the order CV2.imwrite. And then we will write a copy of the image in the folder copy. So look now, the folder copy does not contain anything. And now let me execute the code. And here there are several ways on how we can execute the code. So now I'm in Rust Essentials folder, so I can go to src/topic B. And here I have all the different Python scripts, so I can run them. So one way to run is to use Python and then the name of the file. So now here the name of the file is OpenCopy. Okay, so this is now the image display. Okay, it's displayed by the command imshow. So, and this is the name of the window image, and this is the image display. And now looking at the copy folder, so there is nothing until I press a key. So let me press a key now, and then this command cv2.imwrite is going to be executed, and we have now a copy. So 3 copies, so it's the same image copied. Okay. So you can see now with OpenCV, we are able to open an image, read it, and then display it on a window. And also, we can copy the image to a file. We can also execute the same code but differently. So instead of writing Python and then the name of the script, we can just type the name of the script directly. So it's OpenCopy like this. Okay. /OpenCopy is executing the copy the script in the current directory, and then it's going to be executed. Okay, so let me press a key. But of course, this one only works only if you have this command in the first line of the script. So look, if I remove this command here, because this one it tells about what kind of script is going to be used for this file. So if I remove it, we want to execute it like this, it's not going to work because we did not specify the type of the script. However, if we use Python and then OpenCopy, it's going to work. So now it depends on how you want to execute it, but if you want to execute it without using Python, so you have to specify the type of the script here as a Python in the first line as a command like this. It's possible to run it without using run because this script is actually doesn't make part of Rust, so you can execute it anywhere, not necessarily inside the Catkin workspace. It can be executed in any location because it's just a Python script. It doesn't have to do with Rust. However, we can still use run to execute it if we want. run, Rust Essentials, and then the name of the script, which is OpenCopy. Okay, and it will also execute because run is going also to run Python. These are the 3 different ways on how we can run the Python. So in this video, I have presented how to open and read an image from a file and how to save it to a file. But now we want to know what is inside this image, what is the content of the image. And this is the objective of the next lecture. In the previous video, I have presented how to open, display, and save an image into a file using OpenCV. That's awesome. But in computer vision applications, we need to process the image. So we need to have access to the pixels, to the different colors, and process them. In this video, I will discuss the structure of an image and how to access the pixels of an image and which data structures are used to store an image and pixels. So let's see how it works. Let us consider the file imagestructure.py. In the previous lecture, we have executed the file using different ways, either using Rosrun or by executing it as a Python script. In this exercise, I'm going to execute the instructions one by one into a Python environment so that to show the impact of each instruction individually. So the first thing we need to do, we need to go to the folder topic 3 perception, because it is there where we have the image folder from which we are going to read images. So let me go to this folder, cd src topic 3 perception. And now I am here. I can execute the file right away, image structure, but I would like to execute the instructions one by one. So first of all, let's go to a Python environment and just type in Python, and the first thing we need to do is to import numpy as MP, which is the data structures that contains multi-dimensional arrays, and multi-dimensional arrays are used to store an image. So this is the structure where we will store an image. When we load it from the file, we will store it into a numpy array. And then we need to import OpenCV to be able to use OpenCV methods, and then we will open the image. So I'm going to open the image called black and white. So img equal cv2.imread, and then we have to specify the name of the image. So the image is located into images folder, and the name is called blackwhite.jpg. Okay, so I have read now the image. So this is the image that we will read. It's an image that contains just two cells, one cell that is white and another one that is black. So I use this simple image so that you can identify the color of the pixels. So basically, the white color is encoded with the value 255, and the black color is usually encoded with the value 0. So we will be able to observe these colors when we print the content of the NumPy array storing the image. So let's now look what is inside the image. So I'm going just to type img, and you can see here, this is the NumPy array that represents the image. It's a multi-dimensional array, and although this image is black and white, it is considered as a colored image. This is why here we have three channels. One channel for blue, red, and green. So we have BRG encoding of the image. For example, 255, 255, 255. It means that all together means a white color. And we can see that the black color is encoded over 0 or very low values, like 2 here, for example. So this represents the first row of the image. Okay, this is the first row of the image, and then the second row, the third row, and so on. So we can also extract other information of the image. So in Python, an image is stored into a NumPy array. We can also determine the type of the image. We can use type img, and here the type is a multi-dimensional array of the NumPy library. It is also possible to find the size of an image, img.size, and here it is equal to 1350 pixels. So what is this number? We can look at the shape of the image. Okay, so and the shape here, it will tell us how many rows, how many columns, and here the number of channels. So for example, this image has 15 rows, 30 columns, and 3 channels. So 15 is also referred to as the length. Okay, so for example, we can write length equal imshape.shape 0 at the first index. Okay, printing the length, so the length will be equal to 15. The width is equal to img.shape, and is the second index. Okay, so we can print the width of the image. In this case, it's 30 columns. And 3 is the number of channels. Okay, and the third index here, and here we have 3 channels. So you can see this number 1350 is just the number of colors inside the image, which is equal to 15 multiplied by 30, 450, multiplied by 3, it gives us 1350. You can also find the length of the image by just typing len image. Okay, it's going to return the length. So there are 2 different ways. Either you can get it with image.shape, or you can also get it with len image. So in Python, it's possible to extract all the information from shape, okay, assigning them to 3 different values, for example, height, width, and channel. So sometimes we can call it length, sometimes we can call it height, okay. So here you can see that it's going to collect the values from image.shape. You can also find the type of the image, img.dtype, okay. So it means here that the elements are encoded as unassigned integer values over 8 bits, and also using the NumPy structure, it is possible to access a row or a column or even a pixel. So for example, if you want to access a pixel at row 10 and column 5, we can do img 10 5. Okay, so img 10 5 is equal to this value here. We can also access the value of a complete row. Okay, so this is the row. These are the values of the 10th row. Of course, it has 30 values because the width is equal to 30. We can also check what is the shape of a row. img, so this is the row number 10, for example, the shape. Okay, so it's 30 rows and 3 columns because 3 is the number of channels and 30 is actually the width or the number of rows here for the row at index 10. It is also possible to slice the image and only look at a single channel at a time. Okay, so for example, if you want to only look at the channel, at the first channel, index 0, you can use img colon, comma, colon, comma, and then you specify which index of the channel. So this returns all the values for the first channel. If you want to return the second channel, it is possible. And if you want to return the third channel, you can change by. I will exit now the Python environment, and if you want to execute this file as a whole, you can do like we did before. Execute as image_structure.py, and here you have all the execution for the different instructions of the script. So based on this example, you can understand that OpenCV is a powerful tool that allows not only to read images but also to represent them into an efficient data structure using the NumPy multi-dimensional array, and then we are able to access every pixel and every color in the pixel of the image. And NumPy is a scientific library that is very powerful and offers a lot of functionalities and a lot of tools to process multi-dimensional arrays. You have also observed that when we load a colored image, it has 3 channels, one for red, one for green, and one for blue. In the next lecture, we are going to have a deeper look into channels, and we will show how to display every channel individually and how also to display an image into different formats like hue, saturation, and value. So in summary, whenever you read an image or you get an image in OpenCV, you can access any of its pixels just by manipulating the NumPy array. In the previous video, we have presented the data structures that manipulate images in OpenCV. We have also analyzed the content of these data structures and shown how to access pixels, rows, and columns into an image. However, an image can be encoded in different ways. In this video, I'm going to give a brief overview about image encoding and how these encoding are working in OpenCV. So there are several types of encoding. However, there are 3 main ones. An image can be encoded into grayscale color, and in this case, we have only one channel of grayscale colors, and the values of the colors will range from 0 to 255. 0 means black, and 255 means a white color. Another type of common encoding is the RGB format, where an image is encoded into 3 channels, red, green, and blue. In the previous videos, we have opened the image in RGB format. But in computer vision and image processing techniques, there are other encodings that facilitates the processing of the image. One of the most important encodings is the hue, saturation, and values, HSV. The hue indicates the type of color that we see in 360 degrees format. For example, red is represented by the value 0 to 60, yellow from 60 to 120, green from 120 to 180, cyan between 180 and 240, blue between 240 and 300, and magenta between 300 and 360. The saturation is an indication of how saturated an individual color is, which is the amount of gray in the color, and it takes values between 0 to 100%. Finally, the value, also known as the brightness, it expresses the brightness or the intensity of the color from 0 to 100%, where 0 is completely black and 100 is the brightest level and reveals the most color. Now let's see how image encoding works with OpenCV. To work on this subject, let's open the file imagechannels.py. Let us consider the following code to open a colored image. So as usual, we need to import NumPy and OpenCV libraries. Then we use imread in order to read a color image. So here we're going to read cree.jpg, and here we specifically specify that we want to read it as a colored image using this flag, and then we will put it into an object color image. Then let us display the color image using imshow and display it into a window. So let me run this code now, image encoding, and this is now the tree image. This is the original image that we read from the file. Now we're going to extract the different channels of the image. This image is composed of 3 channels. As you can see here, we have red, green, and blue. In OpenCV, it is possible to read these channels individually. So let's see how it works. So you can see here the shape of the image is 293, 220, and you have 3 channels, red, green, and blue. So color.shape allows to return the height, the width, and the channels, as I already explained in the previous video. And here we're going to use the function split of OpenCV library applied on the color image in order to split the image into 3 different channels. 1 channel for the blue color, 1 channel for the green color, and 1 channel for the red color. So now every channel will represent an image by itself. For example, now I can print the blue image, meaning the image in the blue channel. Okay, so let me execute the code, and you can see now we have a grayscale image which represents the blue component of this colored image. I can do also the same for the green and for the red images. So now we're going to show the red channel applied to the red component of the image, and then we will also show the green channel applied to the green component of the image. And running the code now, we're going to have 3 different images. Every image will represent a channel. So you can see here we have the original channel. This is the blue channel image, the red channel image, and the green channel image. All these 3 images combined together will result into the original colored image. OpenCV is a very powerful library, and it is very easy to go from one encoding to another. For example, I would like to convert the image into HSV image. That is possible. In this case, we can use the method CVT_color of the OpenCV library applied to the color image, and here we specify which conversion we would like to have. So this flag color BGR to HSV is going to convert the image from BGR format to HSV format. So here we're going to have the complete HSV image. We can split the image into 3 components, hue, saturation, and value, and then we can concatenate. So because HSV are 3 NumPy arrays, so we can use the NumPy library to concatenate these 3 images together and put them into one window. So here we can show hue, saturation, and value into one window. Let's run the code. You can see now this part is the hue, this one is about the saturation, and this one is about the value, the brightness. And of course, these are the 3 channels that we have extracted in the previous operations. It is also possible to convert a colored image into a grayscale image, and this is a transformation very much used in computer vision and image processing because it is simpler to analyze a grayscale image as compared to a colored image. So the operation is also very simple, like we did with HSV. We can do here with gray color transformation. So we use CVT_color applied to the color image, and here we have another flag that is color BGR to gray instead of HSV, and here the image is going to be converted into a gray image. So let's see the execution, and this is our grayscale image now. So one last thing to show is to print the content of the gray image. So you can observe now we have only one channel. So the gray image is encoded only on one channel. However, HSV and RGB are both encoded into 3 channels. So to summarize, in OpenCV, we can open an image and then we can transform it into different encodings, whatever we want to have, RGB color or hue saturation value or also grayscale encoding. OpenCV is really a very powerful library, allowing to do complex tasks like this in just one line of code. Typically in robotics, robots get a continuous feed of images through its camera. So it is mandatory to be able to read a video stream. OpenCV library supports this functionality. It is possible to read video streams from cameras or from video files, and also to save them to some other files. In this video, I'm going to show how we can read a video stream from USB cam and also from a video file. Let us consider the file readvideo.py. So as usual, we need to import NumPy and CV2 library and OpenCV library, and then in order to capture a video stream, we're going to use the method video capture of the OpenCV library. So video capture can be applied either